Hello everyone, I am Rupokde. I am coming back after a long time, and today I am going to discuss a problem related to function analysis and which was asked WB SET 2021 to 2022. So the concept regarding this problem also very important for the upcoming GATE examination and NET examination and Nbhm examination and many others examination also. So first look at the problem and try to understand this kind of problem. Okay, and after that we will try to solve it. So first look at the problem here. So the problem is here, let T be a self-adjoint operator on a Hilbert space H, then which of the following statement is not correct? Okay, so first option is here, inner product of x and tx is real for all x belongs to capital H, and second option is here, norm of t equal to supremum of x belongs to capital H, and norm of x equal to 1, modulus of inner product of x and tx, and third option is here, eigenvalues of capital T if exist are real, and fourth option is here, T is always invertible. Okay, so this problem also depend on the properties of self-adjoint bounded linear operator. So I always start with how to solve this kind of problem. So how to solve? So how to solve? Okay, first we are going to discuss operator on the Hilbert space H. Okay, let capital A be a linear operator on the Hilbert space H. With domain D of A and which is proper subset of capital H. So that is H D of A and this is A to H, then A star is called the self-adjoint, then A star is called the adjoint operator on capital H if and only if inner product of A star x and y, so this is equal to x and a y for all x and y belongs to D of A. Now what is the adjoint operator on the Hilbert space H? So A star is called the adjoint operator on the Hilbert space H of the linear operator A if and only if inner product of A star x and y, and this is equal to inner product of x and ay, and for all x and y belongs to D of A. So this is the definition of the adjoint operator on the Hilbert space H. Now note, for bounded linear operator D of A equal to H. So now T such that or A such that H to H be a bounded operator or bounded linear operator. Okay, bounded linear operator on the Hilbert space H. Then number 1, A is called self-adjoint or Hermitian if and only if A equal to A star, and second is here A is symmetric if and only if inner product of AXY equal to inner product of X and AY for all X and Y belongs to capital H. So clearly from definition a self-adjoint or Hermitian operator is symmetric. And fourth, the operator A is called normal if and only if A star equal to A star A. And fifth, A is called unitary if and only if A star equal to A star A equal to I. Okay, so this is the basic definition of the self-adjoint or Hermitian operator, and the symmetric operator, and the normal operator, and the unitary operator. So this is the basic concept on the what is the adjoint operator, and what is the bounded adjoint operator, and what is the symmetric operator, and what is the self-adjoint or Hermitian operator, and what is the normal operator, and what is the unitary operator. Now we are going to discuss some results on the bounded self-adjoint linear operators. Okay, so now T such that H to H be a bounded linear self-adjoint operator on a Hilbert space H. Then number 1, inner product of X and Tx is real for all X belongs to capital H. Okay, so this is the first result of bounded linear self-adjoint operator on the Hilbert space H. Now how we prove that inner product of X and Tx is real for all X belongs to H? So solution. So first I take here inner product of X and Tx, and this is equal to T star X and X by use the property of the adjoint operator. So this is equal to Tx and X. Why? Because T is also the self-adjoint bounded linear operator. So this is equal to, so T is equal to T star. Use this property, we get T star, inner product of T star and X equal to inner product of T and X, and this is equal to inner product of X and Tx bar. Clear? So ultimate we get here inner product of X and Tx. So this is equal to inner product of X and Tx bar, and this also hold for all X belongs to capital H, and this imply and this imply inner product of x and tx is real for all x belongs to H. Okay, so if you don't know this result, you can solve the problem according to this concept. Okay, now so we prove that inner product of x and tx is real for all x belongs to x. So this is the first property on the bounded linear self-adjoint operator on the Hilbert space H. Now we are going to discuss the second property of T. Clear? Now what is the second property? So second property is here norm. Now what is the norm on the bounded linear self-adjoint operator on the Hilbert space H? So the norm also defined by norm of T equal to supremum of x belongs to capital H and norm of x equal to 1 modulus of inner product of x and tx. Okay, so this is the norm on the bounded linear self-adjoint operator on the Hilbert space H. Okay, so using these two results, we see that option A and option B are also correct. Okay, now look at the third option. So the third option say that eigenvalues of capital T if exist are real. Okay, now how we prove this result? Okay, so look at here. So third result is here, eigenvalues of T if exists are real. Okay, so solution. Let lambda be the eigenvalues, lambda be the eigenvalue, so lambda be the eigenvalue of T corresponding the eigenvector V and V each are not equal to 0. So ultimate you get here T of V equal to lambda of V. Got it? Now lambda into inner product of V and V. So this is equal to lambda V and V. And what is lambda V? Using the relation 1, I write here. So this is equal to nothing but T of V and V. So this is equal to, now I use the property of the adjoint operator. We get here V and T star V. Now what is T star V? Now what is T star V? So T star V is equal to here TV. Why? Because T is the self-adjoint operator. So ultimate we get this is equal to inner product of V and TV, and this is equal to inner product of V and T of V. Now what is here T of V? T of V is equal to here lambda V. So ultimately you get this is here lambda V, and this is equal to here lambda bar into inner product of V and V. So ultimately you get here lambda minus lambda bar into inner product of V and V, and this is equal to 0. And here you notice that V is not equal to 0. So since V is not equal to 0, so inner product of V and V is not equal to 0. So ultimate from here you get lambda minus lambda bar, so this is equal to 0, and this is equal to lambda bar, and from this relation we get lambda belongs to R. So third result say that if eigenvalue of T exists, then this must be a real number. Okay, so if you don't know this result, you also try to solve this problem according to this concept. Okay, now look at the fourth option. So fourth option is here T is always invertible. Okay, so T is always invertible if and only if T is equal to T star inverse. And this is if and only if T star equal to T star T equal to I. And this is if and only if T is a unitary operator. So T is invertible if T is a unitary operator. But when you look at the problem say that T only the self-adjoint operator. So the problem say that T equal to T star. So the problem don't say that T equal to T star inverse. Clear? So that means so this does not imply that T is always invertible. Okay? If the problem given that T is a unitary operator, then T is always invertible. But here you notice that T is the self-adjoint operator on the Hilbert space capital H. So that means T may or may not be invertible. So that means the problem is here, which statement is not correct. So that means this statement is incorrect. Why? Because the statement say that T is always invertible. So from here we conclude that T is not always invertible. So T may or may not be invertible. Okay. So this is the way to approach this kind of problem, and I hope you got the idea. And if you don't know the properties of the bounded linear self-adjoint operator on the Hilbert space H, you follow any standard book, clear your basic concept. If you face any problem, write in comment box, or you can also send me mail, and I definitely try to help you. Share and subscribe my channel for more update. And again, thank you.